What if you could leave Earth right now, step into a spacecraft and simply drive through the solar system? Not in some distant future, not as a theoretical possibility, but today, this moment. What if the only question standing between you and the rust-coloured valleys of Mars, the swirling storms of Jupiter, or the icy blue horizons of Neptune was simply, how long would it take? Tonight, we embark on the ultimate space road trip, a journey that will transform your understanding of distance, time, and the sheer cosmic vastness that surrounds our fragile blue home. We will travel not in imagination alone, but through the cold mathematics of orbital mechanics, the patient calculations of mission planners, and the humbling reality that space is far, far larger than our everyday minds can comprehend. Before we begin, I invite you to ground yourself in this moment. Leave a comment below telling us where in the world you're watching from and what time it is where you are. As you type those words, consider this. Light from your screen reaches your eyes nearly instantaneously. Yet light from the sun, travelling at 186,000 miles per second, takes over 8 minutes to reach Earth. And that's just the beginning. To reach Neptune, sunlight must journey for more than 4 hours through the frozen darkness. Time and distance in space do not behave as they do in our cities, on our highways, in the comfortable boundaries of our atmospheric home. Most of us think of the planets as neighbours, celestial bodies that orbit nearby in the grand scheme of the universe. And compared to the stars, they are close, achingly close. Yet the word close loses all familiar meaning when we translate it into travel time. Venus, our nearest planetary neighbour, still lies tens of millions of miles away. Mars, the world we dream of colonising, requires a journey measured not in days or weeks, but in months of silent drift through the void. And the outer giants, Jupiter, Saturn, Uranus, Neptune. These worlds exist in a realm so distant that reaching them demands years of patient flight, gravity assists and technological faith. Here is what makes this journey so surprising. The time it takes to reach each planet does not scale linearly with distance. You might assume that if Mars takes 7 months, Jupiter, being much farther, would take proportionally longer. But space travel operates on a different logic entirely. We do not travel in straight lines. We fall along curved trajectories shaped by gravity. We use planets themselves as cosmic slingshots, stealing momentum from their orbital motion to accelerate without fuel. And perhaps most counterintuitively, sometimes reaching a closer planet takes longer than reaching one farther away. Because the physics of orbital insertion, speed matching, and gravitational capture follow rules written not by convenience, but by celestial mechanics. Tonight, we will visit each planet in order, starting with Mercury, scorched and swift in its tight orbit around the Sun, then drifting outward past Venus's golden storms, pausing at Mars where humanity's future may one day take root. From there, we accelerate toward the giants, Jupiter with its impossible size and radiation-soaked moons, Saturn wrapped in rings of ice and shadow. And finally we press into the outer dark, where Uranus spins on its side, and Neptune churns with winds faster than sound, worlds so remote that radio signals take hours just to whisper back to Earth. But this is not simply a catalogue of travel times and distances. This is a meditation on human ambition, a reminder that every robotic probe we have sent, every spacecraft that has ventured beyond Earth's embrace, carries with it a piece of our curiosity, our longing to see what lies beyond the next horizon. These missions are not just feats of engineering, they are acts of pilgrimage. Each journey reshapes our understanding of what is possible, what is patient, and what it truly means to be explorers in an ancient and indifferent cosmos. As we prepare to depart Earth's orbit, consider this. The International Space Station, orbiting just 250 miles above the surface, takes roughly 90 minutes to circle our planet. Yet to reach even the closest planets, we must travel not hundreds, but millions, or even billions of miles. The scales involved are so vast that our minds naturally resist them. We flatten the solar system in diagrams, shrink it into comprehensible models. But out here, in the actual black, distance becomes a tangible weight, a presence that presses against every calculation and every dream. So settle in, take a breath. If you find wonder in these journeys through time and cosmic distance, please like this video and subscribe so we can continue travelling farther together. Now, let your imagination lift. Let go of the certainty of solid ground, and join me as we drift outward into the silent architecture of our solar system, measuring not just how far these worlds are, but how long it truly takes to reach them. Our voyage begins now. The basics: understanding space travel, speed and distance. Before we journey to Mercury or Mars, before we dream of Saturn's rings or Jupiter's storms, we must first understand the nature of the void between us and them. Space is not just empty. It is vast beyond comprehension, measured in distances that defy everyday understanding. To reach another planet is not like crossing an ocean or flying to another continent. It is to traverse a gulf so immense that our familiar measures of time and distance begin to lose all meaning. On Earth, we measure distance in miles or kilometres. A road trip might span hundreds of miles. A flight across an ocean, thousands. But in space, these units become laughably inadequate. The distance between Earth and Mars alone is not measured in thousands of miles, but in tens of millions. To express such numbers in everyday terms is like trying to count grains of sand on a beach one by one until the numbers blur into meaninglessness. Instead, astronomers use a unit called the astronomical unit, or AU. 1 AU is the average distance between Earth and the Sun, approximately 93 million miles, or 150 million kilometres. This single measurement becomes the cosmic yardstick by which we measure everything else. Mercury orbits at roughly 0.4 AU from the Sun, Mars at 1.5 AU, Jupiter at 5.2 AU. Neptune, the most distant planet in our solar system, orbits at an astonishing 30 AU from the Sun. Each increment represents an ocean of emptiness, a silent expanse where no air, no gravity, and no landmarks exist to guide us. But distance alone does not reveal the true challenge of space travel. To understand how long it takes to reach these worlds, we must also consider speed, and here our intuitions fail us once more. The speeds at which spacecraft travel are so extreme that they redefine what it means to move through the universe. Imagine for a moment travelling to Mars in a car. A typical highway speed on Earth is around 60 mph. At this pace, assuming you could drive in a straight line through the void, the journey to Mars at its closest approach would take roughly 50 years. 50 years of continuous driving, without rest, without stopping, across a road that does not exist. The absurdity of the comparison reveals the first truth of space travel. The speeds of everyday life are meaningless beyond our planet. What if we travelled by airplane instead? Commercial jets cruise at around 500 mph. Faster, certainly, but still hopelessly slow by cosmic standards. At this speed, reaching Mars would take about 6 years. 6 years of uninterrupted flight through a vacuum, a journey that would span the entirety of a child's elementary education. Even the fastest military jets, capable of speeds exceeding 2,000 mph, would require over a year to bridge the gap. Airplanes, for all their speed on Earth, are crawling insects compared to the scales of space. This is why space travel demands rockets. Not just any rockets, but spacecraft capable of velocities that dwarf anything that moves on Earth. Modern spacecraft reach speeds of tens of thousands of miles per hour, propelled by controlled explosions, slingshot maneuvers, and trajectories calculated with mathematical precision. Yet even at these incredible speeds, the planets remain distant, and the journeys stretch across months or years. The fastest spacecraft ever built by humanity is NASA's Parker Solar Probe, launched in 2018 to study the Sun. At its peak velocity, the Parker Solar Probe reaches speeds of approximately 430,000 mph, or about 120 miles per second. To put this in perspective, at this speed, you could travel from New York to Los Angeles in less than 10 seconds. It is a velocity so extreme that the spacecraft must be shielded with a heat-resistant barrier capable of withstanding temperatures exceeding 2,500 degrees Fahrenheit. At such speeds, even the near vacuum of space becomes a hazard as individual particles strike the hull with the force of tiny bullets. Yet even the Parker Solar Probe, the fastest object humanity has ever launched, would still take months to reach Mars and years to reach the outer planets. Speed alone is not enough. The universe is simply too vast, too indifferent to our ambitions. Other spacecraft have achieved remarkable velocities through different means. The Voyager 1 and Voyager 2 probes, launched in 1977, are among the fastest human-made objects still travelling through space. After decades of acceleration, including gravitational assists from Jupiter and Saturn, Voyager 1 now travels at roughly 38,000 mph relative to the Sun. It is currently more than 14 billion miles from Earth, the most distant object humanity has ever sent into the cosmos. Yet its journey to reach the edge of interstellar space took over 35 years. 35 years of continuous travel, without pause, without rest, through a darkness so complete that the Sun itself appears as nothing more than a bright star. These speeds are extraordinary, but they are also humbling. They remind us that even our fastest machines are slow when measured against the scale of the solar system. Light itself, the fastest thing in the universe, travels at 186,000 miles per second, or about 670 million miles per hour. At light speed, you could circle the Earth 7.5 times in a single second. Yet even light takes over 8 minutes to travel from the Sun to Earth. To reach Neptune, light requires more than 4 hours. If we could somehow build a spacecraft that travelled at the speed of light, a physical impossibility by the laws of physics, it would still take hours to cross the outer solar system. But space travel is not simply a matter of pointing a rocket at a distant planet and accelerating in a straight line. The cosmos does not work that way. Planets are not stationary targets. They orbit the Sun, constantly moving, constantly shifting positions relative to Earth. Mars, for instance, completes an orbit around the Sun every 687 Earth days. Earth completes its orbit in 365 days. This means that the distance between Earth and Mars is never constant. At its closest approach, known as opposition, Mars is roughly 35 million miles away. At its farthest, when the two planets are on opposite sides of the Sun, the distance swells to over 250 million miles. This perpetual motion introduces a profound complexity to space travel. We cannot simply aim at where a planet is now. We must aim at where it will be months from now, when our spacecraft finally arrives. Every trajectory is a prediction, a carefully calculated arc through space that accounts for the motions of both the departure point and the destination. Miss by even a small margin, and the spacecraft will sail past its target, lost in the void. This is where the elegance of orbital mechanics comes into play. To travel efficiently between planets, spacecraft use what are called Hohmann transfer orbits, named after the German engineer Walter Hohmann, who first described them in 1925. A Hohmann transfer is the most fuel-efficient path between two circular orbits. It involves accelerating the spacecraft at precisely the right moment so that it enters an elliptical orbit that intersects both the orbit of Earth and the orbit of the target planet. The spacecraft coasts through most of the journey, using gravity and momentum, only firing its engines at the beginning and end of the transfer. This method is slow but efficient. A Hohmann transfer to Mars, for example, takes approximately 9 months. To Jupiter, nearly 2 years. To Neptune, over 12 years. The journey is not a sprint, but a patient dance with gravity, a choreography of orbits timed to the movements of worlds. The spacecraft does not fight the forces of the solar system, it surrenders to them, becoming part of the cosmic ballet. Yet there are times when speed is more important than efficiency. For missions that require faster travel, spacecraft can use more fuel or take advantage of gravitational assist from other planets. A gravity assist, also called a slingshot maneuver, allows a spacecraft to gain speed by passing close to a planet and stealing a fraction of its orbital momentum. This technique was used by the Voyager missions, and more recently by NASA's New Horizons probe, which used Jupiter's gravity to accelerate toward Pluto. These maneuvers can shave years off a journey, but they require precise timing and alignment. The planets must be in the right positions, a cosmic alignment that occurs only at certain intervals. The reality of space travel is that every mission is a compromise between speed, fuel, and time. We cannot simply blast off whenever we wish. We must wait for launch windows, specific periods when the planets align favourably, when the trajectories are mathematically possible. Miss a launch window, and the next opportunity may not come for months or even years. This is why space missions are planned years, sometimes decades, in advance. Every calculation, every trajectory, every manoeuvre is choreographed with the precision of a symphony, timed to the rhythms of orbits that have been turning since the solar system was born. For the purposes of understanding how long it would take to reach each planet, we must establish a baseline. Throughout this journey, we will assume the use of modern chemical rockets, similar to those that have carried missions like Cassini, Juno, and New Horizons. These spacecraft typically travel at speeds ranging from 20,000 to 40,000 km/h, depending on the mission profile and the use of gravitational assists. We will also assume the use of Hohmann transfer orbits for most destinations, the most fuel-efficient and commonly used method for interplanetary travel. With these assumptions, we can begin to grasp the true scope of reaching each planet. Mercury, scorched and closest to the Sun, is paradoxically difficult to reach, requiring precise deceleration to avoid overshooting into the Sun's gravity well. Venus, shrouded in clouds, is closer but equally hostile. Mars, our most familiar neighbour, still demands months of travel. And beyond Mars, the outer planets loom, each requiring years of patient voyaging through the cold and dark. But the question remains, which planet takes the longest to reach? Which is the shortest? The answers are not as simple as distance alone might suggest. Orbital mechanics, planetary positions, and mission objectives all play a role. Some planets, though farther, are easier to reach due to favourable alignments. Others, though closer, require more energy and time due to their orbits. As we prepare to visit each world in turn, we carry with us this understanding. Space is not merely distance, but time stretched across the void. Every mile is a moment, every planet a milestone in a journey that tests the limits of patience, ingenuity, and human ambition. The cosmos does not reveal its secrets quickly. It demands that we slow down, that we calculate, that we wait. And in that waiting, in that slow passage through the dark, we come to understand not just the planets we seek, but the nature of exploration itself. Ahead of us lies Mercury, the sun-scorched sentinel of the inner solar system. Behind us, the familiar blue sphere of Earth begins to shrink, a pale dot fading into memory. The journey has begun. The clock is ticking, and the universe, vast and patient, waits for us to cross the distances that separate one world from the next. Mercury and Venus, our scorching inner neighbours. Before we venture toward the outer solar system's frozen giants, we must first look inward toward worlds bathed in the sun's relentless fire. Mercury and Venus, our closest planetary neighbours along with Mars, orbit in realms of extreme heat and crushing pressure. They are the scorched siblings of Earth, planets so near and yet so forbiddingly hostile that reaching them requires not just courage, but precision beyond measure. Distance, we assume, equals time. The closer the destination, the shorter the journey. But in the physics of space travel, proximity is deceptive. Mercury and Venus teach us that the shortest path is not always the fastest, and that travelling inward toward the Sun can be far more complex than journeying outward into the cold, dark beyond. Mercury, the smallest planet in our solar system, orbits at an average distance of just 48 million miles from Earth. Venus, shrouded in clouds of sulfuric acid, passes within 25 million miles of our world at its closest approach, making it our nearest planetary neighbour. By cosmic standards, these distances are trivial. Yet reaching these worlds has proven to be one of the greatest challenges in planetary exploration. The reason is gravity, the invisible architecture of the solar system that dictates not just where we go, but how we must travel to arrive. To reach Mercury, paradoxically, takes longer than reaching Mars, despite Mars being nearly twice as far away. NASA's Messenger spacecraft, launched in 2004, took 6.5 years to reach Mercury, a journey that required 6 planetary flybys, 3 past Mercury itself, 2 past Venus, and 1 past Earth. It travelled not in a straight line, but in an intricate spiral, gradually bleeding off velocity to match Mercury's blistering orbital speed of nearly 30 miles per second. Without these gravity assists, Messenger would have screamed past Mercury, unable to slow down, forever trapped in an orbit around the Sun. This is the puzzle of travelling inward. As we fall toward the Sun, we accelerate. Our spacecraft gains speed not from its engines, but from the Sun's immense gravitational pull. To reach Mercury and enter orbit, we must shed that velocity, fighting against the very force that drew us there. It is like trying to gently land on a moving train while falling from the sky. Every mile closer to the Sun increases the challenge exponentially. In theory, with enough fuel, we could reach Mercury in a matter of months by simply firing our engines continuously to counteract acceleration. But fuel is mass, and mass is the enemy of space travel. No rocket yet built could carry enough propellant to make such a journey practical. Instead, we must rely on patience and precision, using the gravity of planets as invisible brakes, slowly adjusting our trajectory through a cosmic ballet measured not in days, but in years. If you could somehow drive to Mercury at highway speeds, travelling at 60 miles per hour without stopping, the journey would take approximately 91 years. If you could board a commercial airliner travelling at 550 mph, you would arrive in a little under 10 years. But even aboard the fastest spacecraft humanity has ever launched, the Parker Solar Probe, which reaches speeds of 430,000 as it dives past the Sun, Mercury remains a destination that demands years of careful navigation. Yet, the journey to Mercury is not simply about overcoming distance. It is about descending into an environment where the laws of survival are rewritten by proximity to a star. As we approach Mercury, the Sun swells in the sky, growing larger and more menacing with every passing day. Temperatures on Mercury's sun-facing side soar to 800 degrees Fahrenheit, hot enough to melt lead. On its night side, temperatures plummet to minus 290 degrees, creating the most extreme temperature variation of any planet in the solar system. There is no atmosphere to cushion our arrival, no clouds to obscure the scorched surface below. Mercury is naked rock, ancient and cratered, a world hammered by meteorites and baked by unfiltered solar radiation. The spacecraft that reach Mercury must be engineered to withstand this dual assault of heat and cold, equipped with sun shields and radiators that can dissipate temperatures capable of destroying electronics in seconds. As we enter orbit, we see a world of iron and stone, its massive iron core making up 85% of its radius, larger proportionally than any other planet. Mercury is dense, heavy, and ancient, a relic from the violent birth of the solar system when planets were forged in collisions of unimaginable power. To stand on Mercury's surface would be to experience time differently. A single day on Mercury lasts 176 Earth days, nearly 2 Mercury years, because the planet rotates so slowly. If we watched the sun rise, it would take weeks to climb above the horizon. In some regions, the sun would appear to reverse direction mid-sky, rising, setting, and rising again due to Mercury's eccentric orbit. Time here is not linear. It bends and loops like the gravity wells we travelled through to arrive. Venus, by contrast, is closer and yet equally enigmatic. At its nearest approach, Venus is a mere 25 million miles away, less than half the distance to Mercury. Reaching Venus should be easier, and in some ways, it is. The Soviet Union's Venera missions in the 1960s and 70s took between 4 and 5 months to reach Venus, with Venera 7 completing the journey in 120 days. NASA's Magellan spacecraft, launched in 1989, arrived in just 15 months after using a gravity assist from Earth to gain the necessary velocity. More recently, NASA's Parker Solar Probe has performed multiple flybys of Venus as part of its mission to study the Sun, using the planet's gravity to adjust its trajectory. Each flyby takes only months to reach from Earth, demonstrating that when alignment and mission design permit, Venus is a destination within relatively easy reach. If you could drive to Venus at 60 mph, the journey would take approximately 47 years. By airplane, you would arrive in just over 5 years. Aboard a spacecraft like the Parker Solar Probe, Venus can be reached in a matter of months, making it one of the most accessible planets in terms of pure travel time. And yet, despite its proximity, Venus remains one of the least explored worlds in our solar system. Fewer missions have been sent to Venus than to Mars or even the outer planets. The reason is not distance, but destination. Venus is a planet that destroys those who visit. Hidden beneath its thick clouds of sulfuric acid lies a surface where the atmospheric pressure is 90 times greater than Earth's, equivalent to being 3,000 feet beneath the ocean. Temperatures at the surface reach 900 degrees Fahrenheit, hotter than Mercury despite being nearly twice as far from the Sun. This hellish heat is sustained by a runaway greenhouse effect, where carbon dioxide traps solar radiation, turning the planet's atmosphere into a furnace. No sunlight penetrates the cloud deck. The surface of Venus exists in perpetual twilight, illuminated only by the faint orange glow of superheated air. The Soviet Venera landers, the only spacecraft to successfully land on Venus and transmit data, survived for mere minutes before being crushed and incinerated by the planet's brutal environment. Venera 13, the most successful, lasted 127 minutes on the surface, long enough to capture the only photographs ever taken from the ground of another planet in our inner solar system. The images reveal a landscape of flat volcanic plains, sharp rocks, and a sky the colour of burnt copper. It is a vision of Earth's possible future, a world that may once have had oceans, perhaps even life, before a catastrophic climate shift turned it into an inferno. Travelling to Venus is a journey not just through space, but into an alternate reality of what Earth could become. As we approach, the planet grows larger, filling the view with swirling white clouds that rotate around the planet once every 4 days, far faster than the planet itself rotates. Venus takes 243 Earth days to complete a single rotation, and it spins backward, opposite to nearly every other planet. A day on Venus is longer than a year. The sun rises in the west and sets in the east, drifting slowly across a sky that never clears. If we could descend through the clouds, we would pass through layers of sulfuric acid droplets that fall like rain but evaporate before reaching the ground. The air thickens with every mile. Pressure mounts until it feels not like atmosphere but like liquid. The spacecraft shudders under the strain. Heat radiates from all directions, not from the sun above, but from the ground below, baked and glowing with trapped thermal energy. At the surface, the landscape is alien yet strangely familiar. Volcanoes rise in the distance. some possibly still active, releasing fresh lava across plains that stretch beyond the horizon. Mountains taller than Everest pierce the hazy sky, their peaks lost in the oppressive atmosphere. Rocks glitter faintly with a metallic sheen, minerals that exist only under extreme heat and pressure. The wind is slow, almost imperceptible, yet powerful enough to erode stone over eons. There is no water, no ice, no relief, only heat, pressure, and silence. The journey to Venus reveals something profound about planetary destinies. Earth and Venus are nearly identical in size and composition. They formed from the same material at nearly the same time in nearly the same region of the solar system. Yet one became a cradle for life, and the other became a cautionary tale. The difference is subtle, a matter of distance from the sun, the presence of liquid water, the development of plate tectonics. Small changes amplified over billions of years transform worlds. Standing in orbit above Venus, gazing down at its cloud-shrouded face, we realize that proximity is not the same as accessibility. Venus is close enough to touch, yet unreachable in the ways that matter. We can send probes, capture images, measure temperatures and pressures, but we cannot walk its surface, breathe its air, or linger in its embrace. Venus is a neighbour we can visit but never inhabit, a world that reminds us that distance is more than miles. It is measured in survivability. The journeys, too, Mercury and Venus, are lessons in humility. Despite being the closest planets to Earth, they remain some of the most difficult to explore. Mercury demands years of gravitational manoeuvring to reach. Venus destroys nearly everything we send to its surface. These are worlds where time, temperature, and pressure conspire against us, where even the shortest distances require the longest patience. And yet, there is value in these journeys. Mercury teaches us about planetary formation and the structure of cores. Venus teaches us about climate change and the fragility of atmospheres. Both teach us about limits, not just of technology, but of environments. They show us that the solar system is not a collection of destinations, but a spectrum of possibilities. Some worlds are gentle, inviting, others are harsh, forbidding, and some, like Mercury and Venus, are both close and impossibly far. As we leave the inner solar system behind, bound for Mars and the asteroid belt beyond, we carry with us the knowledge that every planet has its price. Reaching them is not simply about speed or trajectory. It is about understanding the forces that shape them, the physics that govern them, and the patience required to navigate a universe that operates on timescales far grander than our own. Mercury and Venus will continue to orbit in their scorching dance around the sun, eternal and unchanging, and we will continue to watch them from a distance, sending our machines to probe their secrets, learning with each mission that the journey inward is just as treacherous, just as wondrous as the journey outward into the dark. Mars, the most accessible distant world. Of all the worlds beyond our own, Mars stands alone, not the closest, not the largest, but the most beckoning, a rust-coloured beacon in the night sky that has captured human imagination for millennia. Unlike Venus, shrouded in acid clouds, or Mercury, scorched by relentless solar fire, Mars whispers of possibilities, of ancient rivers that once carved valleys into red stone, of polar ice caps that might one day sustain human life, of a world that, though cold and thin of atmosphere, feels somehow within reach. Mars is the most accessible distant world in our solar system, not merely because of proximity, but because of timing, physics, and the alignment of celestial mechanics that make it uniquely reachable. To understand the journey to Mars is to understand why humanity has sent more missions to this planet than to any other beyond Earth. It is to comprehend how distance is not just measured in miles, but in windows of opportunity that open briefly and then close for years. The distance between Earth and Mars is not constant, Both planets orbit the Sun at different speeds and along different paths. At their closest approach, during what astronomers call opposition, Mars lies approximately 34 million miles from Earth. At their farthest, when the planets are on opposite sides of the Sun, that distance swells to over 250 million miles. This cosmic dance determines everything about our journey. We cannot simply point a spacecraft at Mars and go. We must wait for the moment when the trajectories align, when the journey becomes not just possible, but efficient. This moment arrives roughly every 26 months, a launch window brief and precious, when Earth and Mars are positioned in such a way that a spacecraft can reach the red planet without expending impossible amounts of fuel. Miss this window, and you must wait more than 2 years for the next opportunity. This rhythm governs all Mars exploration. It is the heartbeat of our ambitions, the cosmic clock that dictates when we can reach out and touch another world. The first successful mission to Mars was Mariner 4, launched by NASA in November 1964. It took 228 days, just over 7.5 months, to complete its flyby of the red planet. Those months were an eternity of uncertainty. Engineers on Earth watched telemetry data crawl across screens, waiting to see if the spacecraft would survive the journey. When Mariner 4 finally transmitted its images, grainy black and white photographs of a cratered, desolate surface, humanity saw another world up close for the first time. The journey had taken months, but in those moments of revelation, the distance felt immeasurable. Since then, dozens of missions have followed, each one a testament to human persistence and ingenuity. Mariner 6 and 7 took similar paths in 1969, arriving after journeys of 5 months. The Viking missions of the 1970s, massive landers designed to search for life, took nearly a year to reach Mars. Pathfinder in 1997, with its small rover Sojourner, completed the journey in 7 months. Spirit and Opportunity, the twin rovers that would go on to explore Mars for years beyond their planned missions, each took about 6 months to arrive in 2004. More recently, the Mars Science Laboratory mission carrying Curiosity launched in November 2011 and touched down in August 2012, a journey of approximately 8.5 months. Perseverance, the most advanced rover ever sent to another world, launched in July 2020 during the pandemic and landed in February 2021 after a 7-month voyage. Each mission follows a carefully calculated trajectory called a Hohmann transfer orbit, the most fuel-efficient path between 2 planets. This route takes advantage of orbital mechanics, allowing spacecraft to coast through space with minimal propulsion, letting gravity and momentum do most of the work. The travel time to Mars, typically ranging from 6 to 9 months depending on the specific trajectory and the positions of the planets, has remained remarkably consistent across decades of exploration. This is not because we lack faster technology, but because we are constrained by the physics of chemical propulsion and the immense distances involved. Current spacecraft reach speeds of approximately 24,000 miles per hour relative to Earth. At such velocities, crossing tens of millions of miles still requires months of patient travel through the void. But what if we could go faster? To truly grasp the distance to Mars, consider this. If you could drive to Mars in a car travelling at highway speed 60 miles per hour without ever stopping, the journey would take approximately 65 years at Mars' closest approach, an entire human lifetime spent behind the wheel. If you flew in a commercial airliner at 500 miles per hour, it would still take nearly 8 years of continuous flight. Even at the speed of a spacecraft, 24,000 miles per hour, the journey requires half a year. Only light itself, travelling at 186,000 miles per second, could make the trip in a matter of minutes. At closest approach, light takes just over 3 minutes to travel from Earth to Mars. At its farthest, that light travel time extends to about 22 minutes. A signal sent from Earth takes that long to reach Mars, and another identical period for a response to return. Conversations across interplanetary space are not dialogues, but letters sent into the dark, their answers delayed by the speed of light itself. This delay is more than a technical challenge. It is a psychological one. Astronauts travelling to Mars will be farther from home than any human has ever been. For the first time in history, Earth will not be a blue marble visible through a spacecraft window, but a pale blue dot barely distinguishable from the stars. Help, if needed, cannot come quickly. Communication occurs in half-hour cycles. The journey is not just long in distance, but in isolation. The physical challenges of such a voyage are profound. 6 to 9 months in microgravity causes muscle atrophy and bone density loss, despite rigorous exercise regimens. Cosmic radiation, no longer shielded by Earth's magnetic field, bombards the spacecraft and everyone inside it. Solar storms, unpredictable and powerful, pose constant danger. The psychological toll of confinement in a small spacecraft, with the same handful of people, knowing that any mistake could be fatal, test the limits of human endurance. The journey to Mars is not a vacation. It is an ordeal, a trial by isolation and time. Yet humanity is not content with the current timeline. Visionaries like Elon Musk have proposed dramatically reducing travel time to Mars. SpaceX's Starship, still under development, is designed not just to reach Mars, but to do so faster and carry more cargo and crew than any previous mission. Musk has set an ambitious goal, reducing the journey to 30 days or less. Such a timeline would revolutionize Mars exploration, transforming it from an expedition requiring years of preparation and endurance into something approaching a long-haul flight. But achieving this requires technology far beyond current chemical rockets. Nuclear propulsion systems, both nuclear thermal and nuclear electric, offer one path forward. Nuclear thermal rockets heat propellant using a nuclear reactor instead of chemical combustion, providing significantly higher efficiency and thrust. Such systems could potentially cut travel time to Mars in half, reducing the journey to 3 or 4 months. Nuclear electric propulsion, which uses electricity generated by a reactor to ionize and accelerate propellant, offers even greater efficiency over longer periods, though with lower thrust. These systems could enable faster transits and more flexible launch windows, making Mars more accessible than ever before. Even more ambitious are concepts like fusion propulsion and antimatter drives, technologies still largely theoretical, but not beyond the realm of future possibility. Fusion rockets, harnessing the same nuclear reactions that power the Sun, could accelerate spacecraft to velocities impossible with chemical or fission-based systems. Travel times could shrink to weeks rather than months. Antimatter propulsion, though currently limited by our inability to produce and store antimatter in useful quantities, represents the upper limit of known physics. Such engines could theoretically propel spacecraft at a significant fraction of the speed of light, reducing the Mars journey to days or even hours. But these technologies remain dreams on drawing boards, waiting for breakthroughs in science and engineering. For now, the journey to Mars remains measured in months. Those months are not wasted time, but part of the experience itself. Astronauts will watch Earth shrink behind them, transitioning from a world to a moon, from a moon to a star. They will see the Sun diminish slightly in brightness and warmth as they move outward. They will experience the profound silence of deep space, interrupted only by the hum of life support systems and the quiet rhythm of daily routines designed to maintain sanity and health across the void. The spacecraft becomes a world unto itself, a tiny bubble of air and warmth surrounded by infinite cold and vacuum. Inside, astronauts will exercise, conduct experiments, monitor systems, and prepare for arrival. They will communicate with Earth, knowing each message is delayed by minutes that stretch into longer delays as the distance grows. They will look ahead through small windows, watching Mars grow from a point of light into a disk, then into a world with visible features. The Great Canyon of Valles Marineris, the towering peak of Olympus Mons, the white shimmer of polar ice caps. The journey to Mars is also a journey through human history. Every day of travel is a day farther than our ancestors ever imagined possible. It is a distance measured not just in miles, but in millennia of dreaming. Ancient astronomers watched Mars wander across the night sky and named it for the god of war, noting its blood-red colour. Galileo turned his telescope toward it and saw a disk, not a point. Percival Lowell imagined canals carved by a dying civilization. Science fiction writers populated it with alien cultures and lost cities. Each generation brought Mars closer, not through technology alone, but through imagination and desire. Now, as we stand on the verge of sending humans to Mars within the next decade or two, the journey is transforming from fantasy into logistics. Space agencies and private companies calculate trajectories, plan supply missions, design habitats, and solve the 1,000 technical problems that stand between us and a human footprint in Martian dust. The journey time, 6 to 9 months with current technology, is not a barrier, but a waypoint. It is the necessary crossing between worlds, the price paid in time for the privilege of standing on another planet. As we drift through the months-long journey toward Mars, time becomes elastic. Days blur into weeks, weeks into months. The spacecraft's clock marks each passing hour, but the experience of time changes. There are no sunrises or sunsets to measure days, only the artificial rhythm of scheduled sleep cycles and duty shifts. Outside the small windows, stars remain fixed in their positions, offering no sense of motion. Only the growing presence of Mars ahead provides evidence of progress. The red planet swells slowly, imperceptibly at first, then with increasing clarity as the spacecraft closes the final millions of miles. In those months of travel, astronauts become something new. No longer Earthlings, not yet Martians. They are voyages suspended between worlds, carrying with them the hopes and dreams of an entire planet while moving toward another. The journey to Mars is transformative, not because of where it ends, but because of what happens along the way. In the isolation and silence, humans confront the vastness of space and their own smallness within it. They realize that Earth, for all its conflicts and complexities, is a fragile oasis in an unforgiving cosmos. The accessibility of Mars relative to other distant worlds has made it the focus of our interplanetary ambitions. It is close enough to reach with current technology, yet far enough to challenge us. Its environment, while hostile, is less immediately lethal than Venus or Mercury. Its day is remarkably similar to Earth's, just 37 minutes longer. Its seasons, caused by axial tilt like our own, are recognizable if twice as long. Water exists there, locked in ice and perhaps in subsurface aquifers. The ingredients for life, if not life itself, may be present. Mars offers the possibility, distant but real, of becoming humanity's second home. But to reach it, we must first endure the journey. 6 to 9 months of travel with current propulsion, perhaps 3 to 4 months with near-future nuclear systems, maybe 30 days if Musk's vision becomes reality, or conceivably someday, mere hours if theoretical propulsion technologies mature from dream to reality. Each reduction in travel time makes Mars more accessible, more tangible, more real as a destination not just for robotic explorers, but for human settlers. As we prepare to leave Mars, behind in our cosmic journey, travelling deeper into the solar system toward the gas giants and ice worlds beyond, we carry with us the knowledge that Mars represents a threshold. It is the farthest world we can currently envision reaching with human crews. Beyond Mars, distances stretch not into months, but into years. The journey to Jupiter takes not half a year, but 5 or more. Saturn requires 7. The ice giants, Uranus and Neptune, demand voyages measured in decades. Mars is our stepping stone, our proving ground, the world where we will test whether humanity can truly become a spacefaring species. The time it takes to reach Mars is more than a number. It is a meditation on distance, on patience, on the human capacity to dream of far horizons and then cross them. Every mission to Mars, whether robotic or someday human, is a statement that we are not content to remain on one world, that we will endure months of isolation, risk, and uncertainty for the chance to stand beneath an alien sky and look back at Earth as just another star. Mars waits for us, as it has waited for billions of years. The journey is long, but no longer impossible, and as our spacecraft finally enters Martian orbit, after months of silent travel through the void, we are no longer merely visitors from Earth. We are emissaries of a species learning to navigate the cosmos, one patient month at a time. Ahead lies the red planet itself, with its mysteries and dangers. But behind us lies an even greater journey, the one from Earth to here, measured not just in miles, but in the courage to believe that even distant worlds can someday become home. Jupiter and Saturn, giants of the outer solar system. Beyond the asteroid belt, the solar system transforms. The familiar rocky worlds give way to realms of impossible scale, where planets are not merely larger, but fundamentally different. Here, gravity rules with absolute authority, and time stretches across years rather than months. We have crossed an invisible threshold. Ahead lie Jupiter and Saturn, the twin titans of the outer solar system, worlds so massive they reshape our understanding of what a planet can be. Jupiter looms in the darkness like an ancient god waiting in silence. A journey here is not simply about distance, but about entering a domain where the rules themselves change. What does it truly mean to travel to a world so massive it contains more mass than all other planets combined? How long would it take to reach this colossal sphere of swirling storms and crushing gravity? The answer depends entirely on how we choose to go. Reaching Jupiter is a monumental endeavour, one that has challenged humanity's most ambitious space missions. Depending on the trajectory, technology and approach strategy used, a spacecraft can take anywhere from 13 months to nearly 6 years to arrive at Jupiter's orbit. Each mission tells a different story of time, velocity, and the careful choreography required to navigate the cosmic distances involved. NASA's New Horizons probe, launched in 2006 with a singular purpose to reach Pluto, became one of the fastest objects ever launched by humanity. It reached Jupiter in just over 13 months, covering the distance at blistering speeds exceeding 36,000 miles per hour. New Horizons did not stop at Jupiter. It could not afford to. Instead, it conducted a flyby, capturing stunning images and scientific data while using Jupiter's gravity to accelerate even faster toward the outer reaches of the solar system. For New Horizons, Jupiter was not a destination but a stepping stone, a cosmic highway marker on a journey into the far frontier. Other missions took longer, more deliberate paths. The Galileo spacecraft, launched in 1989, took nearly 6 years to reach Jupiter, arriving in 1995. Its journey was indirect, looping through the inner solar system multiple times, to gather speed through gravity assists from Venus and Earth before finally setting course for the gas giant. Once there, Galileo did what New Horizons could not. It entered orbit, spending 8 years studying Jupiter and its moons in unprecedented detail. The extra time required to reach Jupiter was the price paid for the ability to stay, to observe, to understand. NASA's Juno mission, launched in 2011, took 5 years to reach Jupiter, arriving in 2016. Like Galileo, Juno used gravity assist to build the velocity needed for orbital insertion, swinging past Earth once more before hurtling outward. But Juno's trajectory was designed with precision, placing it into a highly elliptical polar orbit that allowed it to skim just above Jupiter's cloud tops, diving into the planet's intense radiation belts to gather data about its interior structure, magnetic field, and atmospheric composition. Each of these missions represents a different answer to the same question. How long does it take to reach Jupiter? The truth is, it depends on whether you're passing through or planning to stay. A fast flyby can be achieved in just over a year. A careful orbital insertion designed to maximize scientific return, requires years of patient travel through the void. But what if we measured the journey differently? What if, instead of advanced spacecraft, we tried to reach Jupiter using more familiar forms of travel? If you could somehow drive to Jupiter in a car travelling at highway speed, 60 miles per hour, non-stop, without pausing for fuel or rest, the journey would take approximately 1,040 years. Over a millennium behind the wheel, watching generations pass, civilizations rise and fall, all while Jupiter slowly grows larger in the windshield. The distance is simply incomprehensible at human scales. Even aboard a commercial airliner cruising at 500 miles per hour, the trip would still take more than 120 years. Faster, yes, but still far beyond the span of a human lifetime. These comparisons reveal a profound truth. The outer solar system is not designed for human intuition. It exists on a scale that demands technology, patience, and an acceptance that some journeys cannot be rushed. Yet spacecraft do not simply fly directly to Jupiter. They dance with gravity itself, harnessing the invisible pull of planets to multiply their speed without burning a single drop of fuel. This is where the true elegance of space travel reveals itself. Jupiter is not just a destination. It is a gateway, a cosmic accelerator, a slingshot built by nature itself. Its immense gravitational pull acts as a force multiplier, capable of taking a spacecraft travelling at modest speeds and flinging it outward at velocities that would otherwise require impossible amounts of fuel. This technique, known as a gravity assist or gravitational slingshot, has become one of the most critical tools in deep space exploration. The concept is both simple and profound. As a spacecraft approaches Jupiter, it falls into the planet's gravity well, accelerating as it is pulled inward. Instead of crashing into the massive sphere, the spacecraft arcs behind Jupiter, skimming past the planet at precisely the right angle and speed. In doing so, it steals a tiny fraction of Jupiter's orbital momentum as the planet moves around the Sun. To Jupiter, this exchange is imperceptible, a cosmic rounding error. To the spacecraft, it is transformative. Suddenly, without expending fuel, the spacecraft is travelling thousands of miles per hour faster, propelled outward on a new trajectory towards Saturn, Uranus, Neptune, or even beyond the edge of the solar system itself. This method was famously used by both Voyager 1 and Voyager 2. Launched in 1977, these twin spacecraft were designed to take advantage of a rare planetary alignment that occurs only once every 176 years. By precisely timing their journey and using Jupiter's gravity, they gained enough speed to visit multiple outer planets in a single mission. Without the slingshot effect, reaching Neptune alone would have taken more than 30 years. Gravity became a silent engine, one that required no fuel, no maintenance, and has continued to propel Voyager 1 into interstellar space, where it now travels among the stars. The experience of harnessing Jupiter's gravity is unlike any other. As the spacecraft approaches, Jupiter grows rapidly, filling the view with swirling bands of red, orange and gold. The Great Red Spot, a storm larger than Earth, spins slowly beneath the spacecraft's path. Gravity increases, pulling the spacecraft faster and faster. Even though gravity cannot be felt directly in the weightlessness of space, its effects become evident through acceleration. Instruments detect the shift. Clocks tick slightly slower due to time dilation caused by Jupiter's immense mass. We're not simply moving through space. We're moving through the contours of space-time itself. As the spacecraft swings behind the planet, Jupiter fills half the sky, glowing with storms that have raged for centuries. In that moment, suspended between the pull of Jupiter and the forward motion of its orbit, the spacecraft is flung outward. Speed multiplies, the path shifts. What was once a journey measured in decades becomes achievable in years. The spacecraft is now no longer just a visitor to the outer solar system. It is a traveller of the deep beyond, armed with velocity stolen from a giant. Harnessing Jupiter's gravity is a reminder that space travel is not a battle against nature. It is a partnership with it. We do not conquer the cosmos by force, but by learning its rhythms, its patterns, its hidden pathways. Jupiter, the ancient king of planets, becomes our ally, opening the door to the solar system's farthest frontiers and sending us onward toward the ice giants, the frozen moons, and the secrets waiting in the darkness ahead. Farther still, Saturn rises like a dream sculpted from ice and light. Its rings stretch wider than Earth itself. Reaching this world tests the limits of time and human patience. As we leave the gravitational embrace of Jupiter, our spacecraft continues onward, journeying through a realm where sunlight fades into a pale, distant glow. The darkness deepens, but ahead something luminous begins to emerge, a delicate, shimmering halo suspended in space. Saturn, the jewel of the solar system, slowly reveals itself. Unlike any other planet, its beauty is immediate, undeniable, and otherworldly. The rings, made of countless shards of ice and rock, catch the faint light of the sun and scatter it in all directions, creating a cosmic crown that glitters like frozen fire. Reaching Saturn takes time, years, not months. The distance from Earth to Saturn varies as both planets orbit the Sun, but at its closest, Saturn is approximately 746 million miles away. At its farthest, the distance stretches to 1.03 billion miles. This vast separation demands patience, planning, and an acceptance that any mission to Saturn is a commitment measured not in seasons, but in presidential terms, career spans, and the slow passage of years. The fastest spacecraft ever sent to Saturn, NASA's Cassini, took nearly 7 years to arrive. Launched in October 1997, Cassini did not reach Saturn until July 2004. 7 years of travel through the void, propelled by a combination of chemical rockets and carefully orchestrated gravity assists. Cassini's journey was not a straight line. It was a cosmic ballet, a carefully choreographed path that looped through the inner solar system twice, using gravity assists from Venus, Earth and Jupiter to build the velocity needed to reach Saturn and enter orbit. Why did it take so long? The answer lies in the physics of space travel and the limitations of rocket fuel. To reach Saturn directly would require an enormous amount of propellant, far more than any rocket could reasonably carry. Instead, mission planners designed a trajectory that traded time for efficiency. Cassini first flew inward toward the Sun, using Venus's gravity twice to accelerate, then swung past Earth for another boost, and finally reached Jupiter, where the giant planet's gravity provided the final massive push needed to reach Saturn. Each gravity assist added months or even years to the journey, but without them, the mission would have been impossible. The time spent travelling was not wasted. It was invested, carefully calculated to ensure that Cassini arrived at Saturn with enough fuel remaining to enter orbit, adjust its trajectory, and conduct a 13-year mission, exploring the planet, its rings and its moons. Compare this to a hypothetical direct flight. If we could launch a spacecraft directly towards Saturn, without gravity assists, using only chemical propulsion, the journey would still take years, but the fuel requirements would be staggering. A direct trajectory at constant acceleration would require carrying so much fuel that the spacecraft would be too heavy to launch. This is the fundamental challenge of reaching the outer planets. Distance is only part of the problem. The real barrier is velocity, and velocity demands either time or energy, often both. If we tried to reach Saturn using more familiar speeds, the timescales become almost surreal. At the speed of a car travelling 60 miles per hour non-stop, the journey to Saturn would take approximately 170 years, nearly 2 millennia behind the wheel, watching entire civilizations rise and fall, all while Saturn remains a distant point of light. Even aboard a commercial airliner cruising at 500 miles per hour, the trip would still take more than 213 years, far beyond any human lifespan. These comparisons are humbling. They force us to confront the vastness of space, not as an abstract concept, but as a tangible reality. Saturn is so far away that even light, travelling at 186,000 miles per second, takes between 79 and 87 minutes to reach it from the Sun. We live in a universe where even light must wait. Yet despite these distances, we have reached Saturn. We have orbited it, studied it, and even landed a probe on one of its moons. The Cassini mission, which arrived after 7 years of travel, spent 13 years in orbit around Saturn, returning over 450,000 images and revolutionising our understanding of the planet and its system of moons and rings. The time it took to reach Saturn was not a delay. It was the price of admission to one of the most beautiful and mysterious regions of the solar system. Saturn does not rage like Jupiter. It revolves in silence, its rings gently spinning like the slow hands of a celestial clock. The planet exudes a calm, ethereal presence, seemingly untouched by time, yet beneath its golden clouds lies a world of extremes. Winds howl across the atmosphere at speeds exceeding 100 miles per hour. Deep within its core lies a sphere of rock and ice, surrounded by layers of liquid metallic hydrogen that generate a magnetic field. Saturn radiates more heat than it receives from the Sun, powered by the slow, gravitational compression of its massive body. To reach Saturn is to enter a dreamscape suspended in darkness. It challenges our perception of space not as empty, but as full of wonders waiting in the silence. The time it takes to get here is not a delay. It is part of the experience, a slow unfolding of the universe's grandeur. As we drift through Saturn's orbit, preparing to continue our journey even farther outward, we pause to reflect on what we have accomplished. We have travelled for years, covered nearly 1 billion miles, and entered the realm of the gas giants. Yet even now we have only reached the midpoint of our solar system. Beyond Saturn lies a frontier even more remote, even more extreme. Uranus and Neptune wait in the cold darkness, worlds so distant that sunlight arrives as little more than a dim glow. These are the ice giants, the final planetary sentinels before the solar system dissolves into the endless expanse of interstellar space. The journey to Jupiter and Saturn teaches us patience. It reminds us that some destinations cannot be rushed, some wonders cannot be reached without sacrifice. But it also fills us with awe, for we have proven that distance is not an insurmountable barrier. With time, ingenuity, and the help of gravity itself, we can reach even the most remote corners of our cosmic neighbourhood. Ahead lies the true frontier. The journey is far from over. Uranus, Neptune, and beyond. The extreme frontier. Beyond Saturn lies a frontier so remote that sunlight arrives not as warmth, but as a memory. Out here, in the cold reaches where planets drift like frozen sentinels, distance is no longer measured in years, but in the patience of generations. This is the domain of the ice giants, worlds so distant that to visit them is to commit not just a spacecraft, but an era of human history to the journey. Uranus and Neptune wait in the darkness, spinning silently, untouched by human presence for decades. The question is not just how long it would take to reach them, but whether we have the will to return. The journey to Uranus stands as one of humanity's greatest feats of persistence. When Voyager 2 was launched in 1977, it carried with it the hopes of a generation eager to glimpse worlds that had only been seen as pale dots through telescopes. The spacecraft travelled for 8.5 years before arriving at Uranus in January 1986. 8.5 years, more than 3,000 days hurtling through the void, passing Jupiter, Saturn, and finally arriving at a world so cold and distant that its surface receives just 1/400th the sunlight that Earth does. Uranus is unlike any planet we have encountered. It is tilted on its side, rotating at a nearly 98-degree angle to its orbital plane, as if the planet was knocked over by some ancient cosmic collision and never recovered. This peculiar orientation means that Uranus experiences seasons lasting more than 20 years, with each pole spending decades in continuous sunlight, followed by decades of darkness. When Voyager 2 arrived, it found a world wrapped in pale blue-green clouds of methane and hydrogen, eerily smooth and featureless compared to the turbulent storms of Jupiter and Saturn. The distance alone is staggering. Uranus orbits at nearly 1.8 billion miles from the Sun, almost twice as far as Saturn. At this distance, radio signals from a spacecraft take more than 2.5 hours to reach Earth. Every command sent must be planned with extraordinary precision, because by the time we receive confirmation that it was received, 5 hours will have passed. Communication becomes not a conversation, but a message cast across time itself. Yet what is perhaps most remarkable about Uranus is not what we discovered, but what we have chosen not to pursue. Voyager 2 remains the only spacecraft ever to visit Uranus. Since that brief flyby in 1986, nearly 4 decades ago, no mission has returned. The ice giant drifts in its distant orbit, unseen by human instruments except through the blurred gaze of telescopes billions of miles away. Why has no one returned? The answer is as much about economics and priority as it is about distance. Missions to Uranus require years of travel time, decades of planning, and technology capable of operating in some of the coldest, darkest conditions in the solar system. Funding such missions means committing resources for timelines that extend beyond political cycles, beyond careers, sometimes beyond lifetimes. But the silence surrounding Uranus will not last forever. Plans are being drafted, proposals submitted. Scientists speak of returning, of sending an orbiter that could study the planet, not for hours, but for years. Such a mission would take at least a decade to reach Uranus, possibly longer, depending on the trajectory and propulsion systems used. With current technology, even the fastest spacecraft would require between 10 and 15 years to arrive. A decade and a half. Enough time for a child to grow into adulthood while waiting for the first images to arrive. As daunting as Uranus may be, Neptune represents an even greater test of human ambition and patience. Voyager 2, after completing its flyby of Uranus, continued onward into the deeper void, travelling for another 3.5 years before finally reaching Neptune in August 1989. In total, the journey from Earth to Neptune took 12 years. 12 years of silent travel through the darkness, crossing nearly 2.8 billion miles of space, propelled only by gravity assists and the momentum gained decades earlier at launch. Neptune is the solar system's most distant major planet, orbiting so far from the Sun that a single Neptunian year lasts 165 Earth years. When Voyager 2 arrived, it revealed a world of breathtaking beauty and violence. Unlike Uranus's placid appearance, Neptune churns with the fastest winds in the solar system, raging at speeds up to 1,200 miles per hour. Its deep blue atmosphere, coloured by methane clouds, is dotted with massive storms, including the Great Dark Spot, a tempest reminiscent of Jupiter's Great Red Spot but colder, darker, and more mysterious. The distance to Neptune stretches comprehension. At nearly 3 billion miles from the Sun, light from our star takes more than 4 hours to reach the planet. Neptune orbits in a realm where sunlight is so dim that standing on its surface, if one could, would feel like perpetual twilight. The Sun would appear as little more than a bright star in a black sky, offering no warmth, no comfort, only a faint reminder of the blazing furnace at the centre of our solar system. To understand the true scale of reaching Neptune, consider this. If we were to send a spacecraft today using conventional propulsion, travelling at speeds comparable to Voyager 2, it would take at least 12 years to arrive. But if we used more advanced propulsion systems, nuclear electric engines or ion drives capable of sustained acceleration, we could potentially reduce that time to 10 or even 8 years. Yet even with these advancements, the journey remains measured not in months, but in decades of mission planning, construction, and operation. Let us imagine the various speeds and what they mean. At 36,000 miles per hour, a typical speed for interplanetary spacecraft, Neptune lies approximately 12 years away. Double that speed to 72,000 miles per hour, and the journey shrinks to 6 years, still longer than many careers in mission control. Even at 100,000 miles per hour, a speed only achievable with gravity assists and advanced propulsion, Neptune would require more than 4 years to reach. There is no fast way to Neptune, there is only patience. Both Uranus and Neptune stand as reminders that the outer solar system is not a place we can casually visit. These are not weekend excursions or brief survey missions, they are commitments. To reach the ice giants is to invest years, sometimes decades, into journeys that may not yield results until long after the engineers and scientists who designed the mission have retired. Yet the rewards are immeasurable. Each of these worlds holds secrets about the formation of our solar system, about planetary atmospheres, magnetic fields, and the behaviour of matter under extreme cold and pressure. Future missions to Uranus and Neptune are not fantasies. They are possibilities waiting for the right moment, the right technology, and the right vision. Proposals have been drafted for orbiters and atmospheric probes, missions that would not merely fly past these distant giants but settle into orbit, studying them for years. Such missions would rely on nuclear power sources, as solar panels become useless so far from the sun. They would need advanced communication systems capable of transmitting data across billions of miles with minimal delay. And they would require something perhaps more valuable than technology: the collective will to wait, to invest, and to trust that the answers we seek are worth the journey. But Neptune is not the edge. Beyond the ice giants lies yet another world, one that captured imaginations for generations before being reclassified. Pluto, the dwarf planet, the distant icy world that orbits in the cold expanse of the Kuiper Belt. When NASA's New Horizons spacecraft launched in 2006, it embarked on a journey that would take 9.5 years. Nearly a decade of travel across more than 3 billion miles of space, moving faster than any spacecraft before it, yet still requiring almost 10 years to reach its destination. New Horizons arrived at Pluto in July 2015, and what it revealed astonished the world. Pluto was not a dead, barren rock. It was a world of towering mountains made of water ice, vast plains of frozen nitrogen, and a thin atmosphere that drifts into space like breath in winter. The images sent back were more than scientific data. They were proof that even at the edge of our solar system, beauty and complexity persist. The time it took to reach Pluto, 9.5 years, represents one of the longest journeys humanity has ever undertaken to a single destination. To put this in perspective, a child born the day New Horizons launched would have been in 4th grade by the time the first images of Pluto arrived. That is how far Pluto is. That is how much patience the universe demands. Now, let us step back and see the full scope of our solar system journey. Let us compare the travel times side by side and witness the staggering scale of distance that separates these worlds. Mercury, our closest planetary neighbour, can be reached in approximately 6 to 7 months. Venus, shrouded in clouds, takes roughly 4 to 6 months. Mars, the red world of future explorers, requires 6 to 9 months depending on orbital alignment. The asteroid belt, that field of ancient stones, takes several months to cross even at high speeds. Then Jupiter, the giant, looms at 13 months to 6 years depending on the mission profile. Saturn, with its glittering rings, demands 6 to 7 years. Uranus, tilted and remote, requires at least 8.5 years, potentially much longer. Neptune, at the edge of the major planets, takes 12 years or more. And Pluto, the distant dwarf, sits waiting 9.5 years away. Each number is not just a statistic, it is a lifetime of planning. It is engineers dedicating entire careers to a single mission. It is scientists waiting decades to see the data they dreamed of as students. It is a testament to humanity's ability to think beyond the immediate, to invest in knowledge that may not arrive until the next generation. But even Pluto is not the end. The true edge of our solar system lies far beyond any planet or dwarf planet. It lies at the heliopause, the boundary where the solar wind from our sun finally gives way to the interstellar medium, the space between stars. Voyager 1 crossed this boundary in 2012, more than 35 years after its launch. It now travels through interstellar space, the first human-made object to leave our solar system entirely. The heliopause sits roughly 11 billion miles from the Sun. To reach it with current technology takes more than 3 decades. Voyager 1 is still transmitting, still sending faint signals back to Earth, though its power source will eventually fade, and one day, perhaps within the next decade, it will fall silent. But even in silence, it will continue onward, drifting through the galaxy, a monument to human curiosity cast into the infinite. To journey to the outer planets, to Uranus, Neptune, Pluto, and beyond, is to embrace a different relationship with time. In the inner solar system, missions are measured in months. In the outer system, they are measured in decades. This is not a limitation. It is a reminder. The universe does not yield its secrets quickly. It requires patience, persistence, and a willingness to look beyond our own lifetimes. Yet the future holds promise. Advanced propulsion systems are being developed. Nuclear thermal rockets, ion drives, and even experimental concepts like fusion propulsion could one day cut travel times in half, or more. What once took 12 years might someday take 5. What took 9 might take 3. We are not bound forever to the speeds of Voyager and New Horizons. We are only bound by what we are willing to imagine, to design, and to build. Uranus and Neptune are not unreachable. They are simply waiting. Waiting for the day when humanity decides that the ice giants, spinning silently in the cold, deserve another visit. Waiting for the moment when we commit once more to the long journey, to the years of travel, to the patience required to cross billions of miles. And when that day comes, when a new spacecraft finally arrives at Uranus or Neptune after years in the void, it will do more than take pictures and collect data. It will remind us that we are capable of extraordinary things, that we can reach across the solar system, across time itself, and touch worlds that exist in realms of cold and darkness we can barely imagine. The extreme frontier is not just a place. It is a challenge. It is a question whispered across the ages. How far are we willing to go? How long are we willing to wait? And what are we willing to sacrifice to know what lies at the edge of our cosmic neighbourhood? In the silence beyond Neptune, in the frozen orbits of distant worlds, the universe waits for our answer. The future of space travel. How we'll get there faster. We have journeyed across vast distances, measured the time it takes to reach worlds of ice and fire, of storms and silence. But as we drift here, suspended between Saturn and the outer darkness, a question emerges from the void. What if the journey could be faster? What if the years we spend crossing the solar system could become months, or even weeks? The future of space travel is not written in stone. It is being forged in laboratories, tested in vacuum chambers, and dreamed into existence by engineers who refuse to accept that distance must forever remain. Our greatest obstacle. The engines that carried us this far are relics of the past. Ahead lies a new era, one where propulsion is not just chemistry, but physics pushed to its limits, where light itself becomes a sail, and atoms become fuel for journeys that span the stars. Nuclear propulsion stands at the threshold of this revolution. It is not a distant fantasy, but a tangible technology that could cut travel times to the outer planets by half, perhaps more. Traditional chemical rockets, the kind that have carried humanity to the moon and beyond, burn their fuel in minutes, expending enormous energy to escape Earth's gravity, then coasting through space for years. They are powerful but inefficient, like sprinting at the start of a marathon and walking the rest of the way. Nuclear propulsion changes the equation entirely. Instead of burning fuel, it harnesses the energy released by splitting atoms, energy so concentrated that a single gram of nuclear fuel contains the power equivalent of tons of chemical propellant. Two forms of nuclear propulsion hold the most promise. Nuclear thermal propulsion heats hydrogen or another propellant using a nuclear reactor, expelling it at temperatures and speeds far beyond what chemical reactions can achieve. The result is a rocket that burns hotter, faster and longer, capable of sustained acceleration that could reduce a journey to Mars from 9 months to as little as 3. To Jupiter, a trip that currently takes years could be completed in under 12 months. Saturn, once a 7-year voyage, might become a 2 or 3 year expedition. The difference is not marginal, it is transformative. Nuclear electric propulsion takes a different approach. Here, the reactor generates electricity, which powers ion engines that accelerate particles to extraordinary velocities. These engines do not roar with flame. They hum with the quiet intensity of precision engineering, producing thrust so gentle it could barely lift a sheet of paper on Earth. But in the vacuum of space, where there is no friction, no resistance, that gentle push compounds over time. Days become weeks, weeks become months, and the spacecraft accelerates continuously, building velocity until it reaches speeds that dwarf anything chemical rockets can achieve. What nuclear electric propulsion sacrifices in initial power, it gains in endurance and efficiency. The true beauty of nuclear propulsion lies in its ability to rewrite the calendar of space exploration. Missions to the outer planets would no longer require decades of planning around narrow launch windows. Travel times would shrink, allowing spacecraft to carry more instruments, more fuel for manoeuvring, and perhaps one day, human explorers who could survive the journey without aging beyond recognition. Nuclear engines are not theoretical curiosities. They are being designed, tested, and prepared for the missions of tomorrow. NASA's Nuclear Thermal Propulsion Project aims to launch crewed missions to Mars using these systems within the next 2 decades. The technology exists, what remains is the will to use it. But nuclear propulsion is only the beginning. Beyond it lies ion propulsion, a technology that transforms electricity into motion with almost supernatural efficiency. The ion drives have already proven themselves in space. NASA's Dawn spacecraft used ion propulsion to visit both Vesta and Ceres in the asteroid belt, a feat impossible with conventional rockets. The principle is elegant. Ionize a gas, usually xenon, then use electric fields to accelerate the ions out of the engine at tremendous speed. The thrust produced is minuscule, but it never stops. An ion drive can fire continuously for years, gradually accelerating the spacecraft to velocities that would astonish the engineers of the Apollo era. Ion engines could revolutionize our understanding of what is reachable. A mission to Neptune, currently requiring over a decade, might be reduced to 5 or 6 years with sustained ion propulsion. The outer reaches of the solar system, once the domain of flyby missions and decades-long odysseys, would become accessible within a human lifetime. More importantly, ion drives use very little fuel. Where chemical rockets must carry enormous tanks of propellant, an ion engine needs only electricity and a modest supply of ionized gas. Paired with solar panels or nuclear reactors, these engines could operate indefinitely, carrying us farther and faster than ever before. Yet even ion drives have their limitations. They excel in the vacuum of deep space, but they cannot lift a spacecraft off the surface of a planet. They are engines of endurance, not power. For missions that require rapid transit, for journeys where time is as precious as fuel, another technology beckons from the edge of possibility. Solar sails, vast sheets of reflective material that catch the pressure of sunlight itself. Photons, though massless, carry momentum. When billions upon billions of them strike a reflective surface, they exert a gentle but continuous force. A solar sail does not need fuel, it needs only light. Imagine a spacecraft unfurling a sail kilometres wide, so thin it is nearly transparent, yet strong enough to withstand the void. As sunlight strikes the sail, the spacecraft begins to move, slowly at first, then faster, accelerating as long as the sun shines upon it. Near Earth, where sunlight is abundant, the acceleration is modest but steady. As the spacecraft moves outward, the pressure diminishes, but by then momentum has already been built. Solar sails could carry probes to the outer planets without a single drop of fuel, drifting on light alone like ancient mariners carried by wind across uncharted seas. But what if we did not rely on the sun? What if we aimed lasers at the sail from Earth or from stations in orbit, beaming concentrated light across millions of miles? Laser propulsion could accelerate a spacecraft to a significant fraction of the speed of light, cutting travel times not by half, but by orders of magnitude. A journey to Mars could take days instead of months. Jupiter could be reached in weeks. The outer planets, once distant and remote, might become regular destinations for robotic explorers and perhaps, eventually, human pioneers. The concept is no longer purely speculative. The Breakthrough Starshot initiative has already proposed using powerful laser arrays to propel tiny spacecraft to Alpha Centauri, the nearest star system beyond our own. If we can aim for the stars, surely the planets are within reach. And yet, for all these advancements, there remains a deeper question. Could we ever move faster than light itself? The answer, as far as physics currently understands, is no. The speed of light is not merely a speed limit. It is a fundamental constant woven into the fabric of space-time. To accelerate a spacecraft to light speed would require infinite energy. Mass itself increases as velocity approaches light speed, making further acceleration exponentially harder. Einstein's theory of relativity is not a suggestion. It is a law carved into the structure of reality. But laws, even those written by the universe, invite creative interpretation. Physicists have proposed theoretical concepts that do not break the light barrier, but sidestep it entirely. Warp drives, inspired by science fiction but grounded in mathematics, suggest that space-time itself could be bent, contracting space in front of a spacecraft and expanding it behind. The spacecraft would not move through space faster than light. Instead, space would move around it, carrying the vessel along like a surfer riding a wave. If such a drive could be built, journeys across the solar system would take minutes, not years. Earth to Neptune could become a trip shorter than a commercial flight. The obstacles are formidable. A functioning warp drive would require exotic matter, substances with negative energy density that have never been observed and may not exist. The energy requirements are astronomical, far beyond anything humanity can currently generate. And even if we solve these problems, the effects on space-time could be unpredictable, potentially dangerous. Warp drives remain firmly in the realm of speculation, a tantalizing possibility that hovers just beyond our grasp. They remind us that the universe still holds secrets, pathways through space and time that we have not yet discovered. For now, we must focus on what is achievable. Nuclear propulsion, ion drives, solar sails, these are the tools that will carry us forward. With nuclear engines, Mars becomes not a distant dream, but a reachable destination for human explorers. A crewed mission to the Red Planet, once thought to require years of space travel and enormous risk, could be completed in a matter of months. The psychological and physical toll on astronauts would be reduced. Supplies would be easier to manage. Communication delays, though, still present, would be less oppressive. Mars, the world that has captivated humanity for centuries, could become the first planet beyond Earth where humans leave footprints in the dust. Jupiter and Saturn, the gas giants that have dominated our imaginations, might also become accessible. Not for landing, their atmospheres offer no solid ground, but for exploration of their moons. Europa, with its hidden ocean beneath a shell of ice. Enceladus, venting water vapour into space from subsurface seas. Titan, with its lakes of methane and skies thick with orange haze. These moons are worlds unto themselves, and they may harbour the ingredients for life. With faster propulsion, missions to these distant shores could be mounted within a decade of planning rather than a generation. Robotic landers could drill through ice, submarines could explore alien seas, and one day humans might stand on the surface of Titan, gazing up at Saturn hanging in the sky like a cosmic lantern. Even the ice giants, Uranus and Neptune, once considered too remote for anything but fleeting flybys, could become subjects of intensive study. A mission using nuclear electric propulsion combined with gravity assists could reach Neptune in 5 years instead of 12. Orbiters could map these worlds in detail, studying their magnetic fields, their atmospheres, their rings and moons. We could finally answer the questions that Voyager 2 left behind. What lies beneath the blue clouds of Neptune? Why does Uranus spin on its side? Are there more moons waiting to be discovered, hidden in the shadows? The future of space travel is not simply about speed. It is about access. Every improvement in propulsion technology expands the map of the reachable universe. Destinations that were once theoretical become practical. Missions that required the careers of entire generations could be completed within a single human lifetime. The solar system, vast as it is, begins to feel less like an ocean to be crossed and more like a neighbourhood to be explored. Each planet, each moon, each asteroid becomes not a distant point of light, but a place we can go, touch, and understand. This transformation will reshape our relationship with space. Today, when we look at the planets through telescopes or study them through the data returned by robotic probes, we are observers. Tomorrow, with faster engines and bolder ambitions, we will become participants. We will not just visit Mars, we will live there. We will not just study Europa's ocean from orbit. We will dive into it. The solar system will cease to be a gallery of wonders viewed from afar. It will become our home, a vast expanse where human presence extends beyond a single fragile world. The expansion of human reach into the solar system will not happen overnight. It will unfold in stages, each breakthrough building on the last. First, robotic missions using nuclear and ion propulsion will pave the way, mapping resources, identifying hazards, and testing technologies. Then, crewed missions to Mars will establish humanity's first foothold on another planet. From there, the journey continues outward. Bases on the moons of Jupiter, research stations orbiting Saturn, perhaps even outposts in the Kuiper Belt, where the sun is a distant spark and the stars shine with unmatched clarity. As we imagine this future, we must also remember the journeys we've already taken. The Voyager spacecraft, launched more than 4 decades ago, are now beyond the edge of the solar system, drifting through interstellar space. They travelled using technology that seems primitive by today's standards, yet they reached their destinations and returned knowledge that transformed our understanding of the cosmos. What will the spacecraft of tomorrow achieve? How far will they go, and how quickly will they arrive? The question we asked at the beginning of this journey, how long would it take to reach each planet, no longer has a single answer. It depends on the technology we choose, the trajectory we plan, and the ambition we bring to the endeavour. With chemical rockets, Mars is 9 months away. With nuclear propulsion, it is 3. With technologies yet to be invented, it may one day be measured in weeks. The distance between worlds is shrinking, not because the universe is getting smaller, but because humanity is learning to move through it with greater mastery. In the end, the future of space travel is not merely a question of engineering. It is a question of vision. Do we see the solar system as an insurmountable expanse, or as a frontier waiting to be crossed? Do we accept the constraints of today's technology, or do we push beyond them, building engines that defy our current limitations? Every spacecraft that launches, every mission that succeeds, Every new propulsion system that is tested brings us closer to a future where the planets are not distant dots of light, but destinations, places where humans can go, explore, and perhaps one day call home. The solar system is vast, but it is not infinite, and with each passing year, with each new advancement in propulsion, it becomes a little more reachable. The future of space travel is not a distant dream. It is unfolding now, in laboratories and launch pads, in the minds of engineers and the aspirations of explorers. The question is no longer if we will reach the far corners of our solar system, but when and how fast we will get there. The journey has only just begun. We have travelled through time and distance, crossing the vast expanse of our solar system, measuring not just miles but moments of wonder. From Mercury, where a journey takes mere months, to Neptune, where the voyage stretches across decades, we have seen that our cosmic neighbourhood is far grander than any single human lifetime can comprehend. The distances are not just numbers, they are epochs, eras, entire chapters of human history compressed into the silence of space. Mercury, our closest planetary neighbour beyond Venus, lies just 77 million miles away at its nearest approach. A spacecraft could reach it in under a year, yet the journey requires precision, timing, and the patience to orbit the Sun itself. Venus, shrouded in acid clouds, is only months away, but to land there is to enter a realm of crushing pressure and searing heat. Mars, the red beacon of exploration, waits 140 million miles distant, reachable in 6 to 9 months, yet every mission there carries the dreams of an entire species hoping to one day walk its dusty plains. But these are the close worlds, the familiar neighbours. Beyond Mars, the scale of distance transforms. Jupiter, the king of planets, demands 13 months to 6 years depending on trajectory and technology. Saturn, with its ethereal rings, requires 7 years of travel, a journey that spans presidential terms, childhood milestones, entire phases of life. Uranus, tilted and frozen, lies nearly 2 billion miles away, reachable only after 8.5 years of silent drift through the void. And Neptune, the farthest true planet, the boundary of our solar neighbourhood, demands 12 years of flight, a voyage that begins in youth and ends in adulthood. These are not distances we can fathom with ease. They stretch beyond imagination, beyond the scale of earthly geography. If we could drive to Neptune at highway speed, the journey would take more than 6,000 years. Even light, the fastest thing in the universe, takes over 4 hours to reach Neptune from the Sun. We are surrounded by vastness, floating on a small blue world in an ocean of darkness so large that it humbles every conception of distance we have ever known. And yet, we have been there. Humanity, in all its fragility, has sent emissaries across these unimaginable gulfs. Voyager 1 and Voyager 2, launched in 1977, have travelled farther than any human-made object, crossing the boundary of the solar system itself and entering interstellar space. These spacecraft carry messages, sounds, images from Earth, golden records meant for civilizations we may never meet. They are proof that distance, however vast, is not insurmountable. Time, however long, is not an obstacle to curiosity. Our place in the cosmic neighbourhood is both humbling and exhilarating. We are small, yes, impossibly small, when measured against the scale of planets, moons, and the infinite dark between them. But we are also capable. We are explorers, dreamers, builders of machines that can cross billions of miles. We're a species that looks at the stars not with fear, but with wonder, and asks not if we can reach them, but when. This journey through our solar system reminds us that perspective is everything. What seems impossibly far today may one day be routine. The distances that stretch across years and decades will shrink as technology advances, as propulsion systems improve, as humanity learns to bend the rules of physics in ways we cannot yet imagine. Future generations may look back at our current spacecraft the way we look at wooden ships crossing oceans, marvelling not at the slowness, but at the courage it took to begin. If this journey has changed the way you see space, if it has stretched your sense of time and distance, let us know by liking this video. Leave a comment telling us where you're watching from on this small blue planet, and which destination surprised you the most. Was it the storms of Jupiter, the rings of Saturn, the silent ice of Neptune? Your perspective matters, and we want to hear it. And if you're hungry for more journeys into the unknown, if you want to continue exploring the mysteries of the cosmos, subscribe to this channel. There are infinite wonders waiting, black holes that warp time, galaxies spinning in the deep, phenomena so strange they challenge the very laws of reality. This is only the beginning. As we close this chapter, remember this. Every planet we've visited today, every moon, every ring, every storm, exists not just in space, but in time. They are ancient, enduring, patient. They have waited billions of years for us to notice them, to reach them, to wonder about them. And one day, perhaps sooner than we think, human footsteps will echo on worlds we have only seen through the eyes of machines. We are small, but we are not insignificant. We are fleeting, but we are not forgotten. We are travellers in the cosmic neighbourhood, and the journey has only just begun.